what are we going to talk about today? We are going to talk about the applications, further applications of Cauchy integral formula for derivatives. So we're going to start with Louville's theorem. Another Louville's theorem. So we talked about a Louville theorem before. Oops. But this is another one. So what's this? Suppose f from the entire complex plane, the complex plane is holomorphic, and bounded. Then f is a constant. Okay, so functions that are holomorphic on the entire complex plane, they're called entire functions, and we'll talk about those later. But the proof of this is quite straightforward. Just from Cauchy's integral formula for derivatives, we just need to apply it for the first derivative. So we know that f prime of z is equal to, so 1 factorial is 1, so it's 1 over 2 pi I. And we're going to take some ball centered around 0 of some large radius, large enough to contain z. So integral bound of the ball. So recall, when I don't put anything here, it means the ball of radius, the ball around 0, right? So whenever I'm not putting brackets at some point, it always means the ball around 0. And what do we know? This is equal to f of zeta, zeta minus z. And since it's one derivative, it's k plus 1, so it's 2 here, d zeta. Yeah, that's Cauchy's integral formula for derivatives applied to the first derivative. So z is some point for any z inside the complex plane where r is bigger than the absolute value of z. Yeah? So this is z saying we're taking any radius bigger than this. Yeah. So what can we do? Well, if we just estimate the absolute value, then, as we've learned, we can estimate this thing by just the length of this curve, which is, so we take this 2 pi from here, and then we have this 2 pi r from the length of the curve, and then the supremum of this expression over the curve, right? And then the sup of this thing over the curve. But if we take the absolute value signs of this thing, then since zeta is going around the boundary of the curve, right, the absolute value of zeta, I think I want to take this to be bigger than twice this. Like this. And then what do we have? Then we know that zeta minus z, absolute value, let's bound it from below. This is bigger than zeta minus mod z, right? And we are choosing zeta's on the curve, so that's equal to r. And this guy is less than half of r, right? So if we subtract half of r, then we still have this inequality. So this is bigger than r over 2. Yeah? So when we take the absolute value signs, we take the absolute value sign on this thing, and then the absolute value sign on this thing, and it will be bounded above by the smallest value this can possibly be over the biggest value this can be. Yeah? So I'll write this stuff down. So we have the supremum over the boundary of the ball of the absolute value of f of zeta over zeta minus z squared, absolute value, like this. Yeah? That's just this estimate we've used lots of times. So zeta belongs to this thing. And then the 2 pi's cancel. So we're just going to have R here. And then what is this thing? Well, the supremum of this thing is less than this guy divided by the smallest value that this thing can possibly be. So this is less than the supremum of around the boundary of the ball of absolute value of this thing divided by the smallest thing this can possibly be squared. So it's over 2 squared. Yeah? Cool. And what's that? That is less than 4 over R. And then actually the supremum of f is less than something because we're assuming it's bounded. So the supremum of the entire complex numbers of f of c, like this. Yeah? And that's true for every single R, which is bigger than twice the absolute value of z. Yeah? So since true for all mod R bigger than twice z, this implies that f prime of z absolute value is equal to 0. Yeah, because this thing is finite, that's in the assumptions. We can take R as large as we like. So the absolute value of f prime of z is less than any number that we like. Yeah, so it actually has to be equal to 0. Cool. So thus f prime of z equals 0 for all z, because nothing about this cared about which z we take, right? And that's it. That proves that it's a constant. Yeah. Cool. So very simple proof just from Cauchy's formula for the derivative. Yeah. Cool. Let's do another consequence. Many cool consequences. Next consequence. So corollary. I have difficulty spelling this word. Corollary. Every polynomial I'm going to write the words complex polynomial. I mean, we're doing complex analysis, so everything we're talking about is complex, but just to emphasize it, every complex polynomial has a root. It's not a corollary of Liouville, but it's a corollary of sorry, it is a corollary of Liouville. Take that back. Proof. Okay, so let's let P of z be a polynomial. So it's a polynomial. We can write it from the sum k equals 0 to n of ak z to the k for some complex numbers ak. A0, A1 to AN along with the complex numbers, right? Okay, and suppose it's false. Suppose it doesn't have a root. Does not have a root. So this is the idea. We're going to consider 1 over P of z. Okay. And we will show that this thing is a bounded holomorphic function. Okay. So the first thing to note is that since P of z is never equal to 0, yeah, this thing is complex differentiable for every single z, so it is in itself a holomorphic function. So it's holomorphic on the entire complex plane by the assumption that P has no root. Yeah? Because we know the quotient rule for complex differentiation. We can apply the quotient rule so long as the bottom's non-zero, so everything is cool. Yeah? So it's holomorphic, and we're going to try and show that it's bounded. Yeah, we're going to try and show it's bounded. Actually, we're going to succeed to show it's bounded. Yeah, so we will show one over P of z is bounded. Okay, so I'm going to erase the board. While I do this, I want you to think about how can we show that it's bounded using the fact we're assuming that it doesn't actually have a root. Yeah? That it doesn't have a root. Okay, so we will show there exists a constant c bigger than 0 such that P of z, absolute value, is bigger than c for all z. And once we show that, then 1 over P of z will be a bounded holomorphic function, right? And therefore be a constant. Okay, so we're arguing by contradiction. We have that P of z doesn't have any roots, yeah? But this is obviously a much stronger statement, yeah? Okay, now give me suggestions. How are we going to conclude from the fact that P of z doesn't have roots that this is true? Okay, let's do the most naive type argument possible, right? Suppose we try and argue by contradiction and take a sequence such that this is false. So suppose this is false, so we can, for every number, say 2 to the minus n, we can find a zn such that the absolute value of P of zn is less than 2 to the minus n. No? Yeah? Now, under what circumstances could we get a contradiction from such a sequence? So suppose we have this sequence z1, z2, z3, and so on, where, let's put this in brackets, suppose we have that absolute value P of zn is less than 2 to the minus n. Yeah? Okay. In what way would this give us a problem? In what way would we get a contradiction from this assumption, given that we've assumed that P has no roots? What property did you use there? What property? Continuity of the polynomial. Polynomial was incredibly, it couldn't be a nicer thing than a polynomial, right? Yeah, so polynomial is continuous. So what assumption are you making in that argument, though? What assumption are you making? What did you just say? You said at the point where we have a limit, P of that limit would be 0. I agree. But what assumption is implicit in that? You'd need to have a convergent subsequence. How would you know that this thing gives you a convergent subsequence? If you just have a collection of infinite collection, countable collection of points, when would you know it has a convergent subsequence? If we had an infinite collection in a bounded set, then it would have a convergent subsequence. Yeah? Yeah? If this sequence is a bounded sequence, yeah, then we're fine, because it'll have a convergent subsequence, and the limit of that convergent subsequence will be a point where the thing is actually equal to 0. Yeah? Cool. All right. So the problem is that this thing might not be a convergence. This might not be a bounded sequence, right? It could go off towards infinity. Yeah? Could it go off towards infinity? Yeah? Or could it? Does it have, is that possible? Is it possible that we have a sequence such that this is true? Suppose. And suppose these guys go off to infinity. Is that possible? Even for some subsequence. Is that possible? Think about what we're talking about. I don't know how to spell this. Pos. R gets big, right? So if you're thinking of polynomials on the real line, you can go down. We can have z to the whatever x to the 3, but that's not what we have right here, right? We have a polynomial in the complex plane. Yeah. So recall p of z. Let's put its leading order term, a n z to the n, a n minus 1, z to the n minus 1, and so on and so on and so on. A1 z plus a0. Yeah. Yeah. And if we just had this term right here and nothing else, yeah, and we put the absolute value signs on it, right? The absolute value of z to the n is absolute value of z to the power n, yeah? And as z gets big, that gets big, yeah? So exactly as Laura says, the r blows up as the radius increases, yeah? And we also know that that's the leading order term. So for very large z, i.e. z whose absolute value is very large, this guy is way more significant than this guy, yeah? That's the idea. That's the idea, and it's the correct idea. And then from that idea, we're going to express that in the language of maths to give us a proof. Yeah? Let's see how to do that. So if we look at this, then let's do the following. Let's divide everything by z to the n. So p of z over z to the n, we're just going to have a n, and then all these other guys will be lower order terms, or I should say terms of negative powers. And then so on. A1 is z to the 1 minus n. And then A0 is z to the minus n. Yeah? Yeah? So, for large enough z, by which I mean absolute value of z is large enough, this thing is really small, right? And so is this thing, and so is this thing, and so is this thing. Yeah? So, in particular, p of z over z to the n is bigger than or equal to the absolute value of an minus the absolute value of all of this stuff here. I'm not going to rewrite all of it. Just going to put it in a box. Stuff in the blue box. Yeah? Yeah? And the absolute value of the stuff in the blue box is less than the absolute value. We're just going to use triangle inequality, pass through all of that stuff, right? So it's less than a to the n minus 1, absolute value of z to the minus 1, plus, let's just do dot, 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 plus dot, 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 absolute value of a1, absolute values here, absolute value of z to the 1 minus n, plus absolute value of a0, mod z to the minus n. These coefficients, a1, a2, an, whatever, they're just numbers, whatever they are, you know, they're just numbers. So we can make mod z big enough so that it makes this term small, this term small, this term small, all these terms small, yeah? Yeah, so this can be less than absolute value of an over 2 for all mod z bigger than some radius r, or r0, which depends on our coefficients. So the way we write constants depending on other things, we write like this. So R0, which depends on coefficients A1, A2, blah, 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 an, and also depends on the number n itself. Yeah? There's clearly some constant for which, for any absolute value of z bigger than R0, then the sum of all of these guys is less than this number right here. Do you see what I mean? Yeah? Cool. All right, so that being the case, let's call this inequality star. So from star, we have that this guy minus something which is less than an over 2 means that p of z over z to the n is bigger than the absolute value of an over 2 for all mod z bigger than R0, yeah? Yeah? And that's equivalent to saying that p of z is bigger than an mod z to the n over 2 for all z bigger, let's make it just bigger than this thing, 0, yeah? And in particular, therefore, p of z can't be equal to 0 if the absolute value of z is bigger than R0. Yeah? You see what I mean? Yeah? And that was just the idea Laura had, but all I did here was express it in the language of maths, right? Yeah? And that's one of the things you people have to learn, that you will hopefully be able to visualize this stuff, have the pictures in your head, which gives you the reason why this stuff is true, but then you have to express those reasons, you have to express your thinking in this language. And that's something you already know how to do to some extent, but that's something you're going to have to learn to do more and more, better and better. Yeah? But you really do have to do that. It's not enough to have what we call hand-waving arguments. This really nails it down. Every single step of this thing is true, right? We go from one to the other, and there can be no doubt now. Yeah? This is how you check that you have the correct thought process, that you break down you break down your argument, your thoughts into little tiny steps which are absolutely true. You can't have any doubt about them to conclude the thing that you're thinking. Yeah? This is the hygiene of math. Rigor is the hygiene of math. This is how we avoid making mistakes. Okay, cool. So this is true. So we know that if we do have such a sequence, yeah, which is getting smaller and smaller and smaller, assuming that n is large enough, n is such that 2 to the minus n is less than the absolute value of a, that's too many n's. Let's call this sequence AZM, like this. So assuming m is large enough so that 2 to the minus m is less than, say, absolute value of an over 4, right? Then all of those guys from that point onwards have to be inside the ball of radius R0. Yeah? Do you see what I mean? Because outside this ball of radius R0, then we know that this is true. Actually, what I said is not, because we have this coefficient as well. So let's write this formally. So if M0 is such that two to the minus M0 is less than mod an R0 to the n over 4, then we must have that z to the m0 or z to the m belongs to the ball of radius r for all m bigger than or equal to m0. That's what I meant to say. Yeah? Cool. So all of these guys are trapped within some ball, yeah? And therefore they will have a convergent subsequence, and therefore the argument that Jaime told us at the start holds true, yeah? So we'll have a convergent subsequence. Yeah? Z to the km, where Z to the km, this might be hard for you to read, tends to say W, which is also inside the ball, doesn't matter, it's inside the complex plane, yeah? And by continuity, this thing is the limit as m tends to infinity, p of zkm, which is equal to 0 by our assumption here. Yeah? By star. Contradiction, because we argued by contradiction and start again. Yeah, we argued by contradiction and said, suppose there are no roots. Yeah? And we just shown there is a root. Yeah? Cool. So, going back, this means that we know that there is some constant such that this is true. So we've shown this now. We've shown this now. Yeah? 'Cause we've assumed it's false. And from the assumption it's false, we got that p has to have a root. Yeah? Cool. All right. I want to try and complete the argument on one board. So let me erase this thing. Let's call this thing star star. The final thing over here. So I should write contradiction. So, since we have that p of z is bigger than c for some constant c for all z inside the complex plane, 1 over p of z absolute value is less than 1 over c, right? And p, or 1 over p of z is constant, so p of z is constant. By Liouville. And that's the end of it. Yeah? That's the end of it. Cool. Okay. So, all these details are kind of unimportant. The only ideas you need are just to think, okay, if it has no roots, then 1 over p of z is a holomorphic function. Yeah? And then it should seem a natural thought that kind of seems like it would be a holomorphic function that is bounded, because if instead of having no roots we had that the absolute value was less than some constant, then that would be a bounded holomorphic function. And then you think, okay, well, that's actually the case. We will have that if it has no roots, then absolute value of p of z will be bounded below, because as we go out towards infinity, for sure, p of z gets very big, because the leading order term will just dominate everything, and that blows up. Yeah. So any sequence for which we get that absolute value of p of z gets smaller and smaller will have to have a convergent subsequence inside some ball, and that contradicts the assumption we're making, arguing by contradiction that we have no roots. So all of these details are kind of unimportant. They're just expressing those rather simple, rather natural ideas that actually you gave me when I asked you for suggestions. Yeah? So, so hopefully you will have this, you'll be able to do this. If I ask you some question to prove this or some part of this in an exam, you will be able to do that just from having these ideas, these rather natural ideas. Yeah? So having all the theorems in the course, it's just a matter of having a couple of natural ideas about why each theorem is true, and then the rest is expressing those ideas somewhat cleanly, somewhat neatly in this language, which you should be able to do. Yeah? And that's my goal for you. I want you to have all of these theorems just accessible to you. You can explain in detail why they're true because you have the couple of fundamental ideas that prove each one of them. Right? All right, cool. Going to erase the board. We do some more consequences of this. Time. All right, so next corollary. Given any polynomial, any poly dot is now polynomial. Any poly p of z of degree n we can factor it, can find n roots counting multiplicity, which is the same as saying we can factor it. So we can factor it like this. So do you know this notation, this product, the overall product, you've all seen that before, from I equals 1 up to n, some coefficient, some constant here, c, and then z minus zi, like this, where z1, z2, zn are the roots. And they can be the same root repeated a number of times. So I could have that z3, z4, z5 are all the same number, right? Are the roots. Counting multiplicity. So what I just said means that we count multiplicity. And I don't know how to spell that word. Multiplicity. Okay, proof. All right, so same deal. Let's try and prove it together. You started off. How do we begin to prove this? What do we know already? We know it has one root. Yeah? We know for sure it has one root. So we know. Do I want to call them Z? Okay, it's too late. We know there is one root. At least one root. Call it Z1. Yeah? Cool. All right, so let's give ourselves the coefficients for this thing. So it's the sum from k is equal to 0 up to n, ak z to the k. Yeah? And then write that z is equal to z minus z1 plus z1, which is obviously true. Yeah? So then if we consider one of these expressions, z to the k, then that's the same as z minus z1 plus z1 to the k. Yeah? That's a true thing. Yeah? Cool. And then by the binomial theorem, we can write this as a sum. Let's do I equals 0 up to k of k choose I of z minus z1 to the I, and then z1, oops, z1. I is a very bad choice in complex analysis, right? Let's call it j. J. And this z1 to the j. Yeah, just the binomial expansion. We actually don't care about the coefficients, but since we know what they are, yeah, that's just true. Yeah? And z1 is just the root that we know. So it's just a complex number, right? It's just a complex number. Yeah? So, look at this. So this is true. No, they're not. They're not. Thank you. That is false. That would be k minus j. Yeah. Cool. All right. So if we look at this guy over there, right, and we use this thing, yeah, that means that we could rewrite this z to the k as this long expression like this, yeah, long complicated expression, yeah. But remember that z1 we're just thinking of is just some particular complex number. It's chosen, right? It's there. It's fixed, yeah. So for, let's call this thing star. For p written star. We can rewrite where we replace every one of these zk's with this complicated expression. Yeah? And after we do all that stuff, ultimately we're going to have a polynomial in terms of z minus z1. Yeah? Because this is a polynomial in terms of z minus z1. Yeah? So we're summing all these polynomials in terms of z minus z1. Yeah? Do you see what I mean? So ultimately, we can rewrite this like this. Let's call these coefficients now bk. Like this. Yeah? For some other coefficients bk. And the bk will be written in terms of the z1, but the z1 is whatever. It's already just some number. It's just fixed. Yeah? Do you see what I mean? Okay, look at this and tell me some things that we know about the coefficients bk. Some simple things. Don't try and give me some explicit expression. Just tell me some simple things. Tell me some simple things. Yeah, that's yeah. Okay. Yeah, but that's not the simple thing. I don't want to try and give explicit expression to them. Tell me something else. Tell me something elementary about these. What do we know about these representations without thinking about it too much about their individual structure? It's not up to infinity. It is up to n, of course. So notice that the highest power of z minus zk in this expansion is power k, right? So the highest power we're going to get in the new representation is power n, right? Because each one of these guys gets replaced by some polynomial whose highest power is k, right? We still have a degree n polynomial in z minus z1 now, but what is z1? Z1's a root, right? Z1's a root. So what is p of z1? It's equal to 0, right? And what else is it? It'd be 0. So just like how you determine the coefficients of the Taylor series in calculus 2, you just stick in the value, right? Determine firstly the constant term, and then you differentiate, you determine the next term, right? So we determine that B0 is 0. Yeah? Cool. So we don't need to start with this thing. We can start with 1. Actually, let me just be consistent. So let's write this in narrative order. 1 up to n, bk z minus z1 to the k. Okay. Now what? Perfect. So let's factor out a z minus z1. What good did that do me? Why is that good? Good. Perfect. Right. Now this is another polynomial, a different polynomial. It's degree 1 less, right? But by the theorem we've just discussed, this guy too has a root. Yeah? This guy too has a root. Now, polynomial also has a root. Could be the same value, could still be z1, but it has a root, right? For sure it has a root. Let's call it z2. Yeah? And then we'll repeat, yeah? Because then this guy is something that we can write as z minus z2 multiplied by a polynomial of degree n minus 2. Yeah? And then we just repeat the argument. Then repeat. Until we have that p of z is some constant, z minus z1, z minus z2, z minus zn. And that's it, yeah? So we have that there are n roots counting multiplicity. We completely factor this thing, which was, this is how complex numbers were invented. This is the thing that is completely false for factorizing even any polynomial. So even though just quadratics for real numbers, we can completely factor any polynomial. We can find all these roots over the complex fields. Yeah, this is called the fundamental theorem of algebra. Yeah? And it follows pretty easily from the previous theorem, just from this idea that we take arbitrary polynomial, yeah, and we rewrite it as a polynomial in terms of z minus z1, where z1 is the one root that we know. Yeah? That's the one idea. And that straight away gives us there is no constant term because z1 is the root, and then we can factor out. And then just repeat. So again, just one idea. One idea. Or 1.5, I don't know. Yeah? Cool. All right, good. Many strong consequences of Cauchy's theorem. Suppose f is holomorphic in some open set omega, and Zn belonging to omega is a sequence where f of Zn is equal to 0, and the limit as n goes to infinity, Zn is equal to z, which also belongs to omega. Omega is an open set, as always. Then f is identically equal to 0. in omega. Therefore, omega has to be connected. Okay. Okay, proof. All right, so let's think about this. Let's take our domain like this, okay? We have a sequence of points where f of z is equal to 0, and it's converging to some limit point right here. Let's not call it z, let's call it w. So I'm going to use z as the variable. Yeah? Some limit point w. Okay. Now, this isn't going to be a consequence of Liouville's theorem or directly of Cauchy's integral estimates, but it will be a consequence of something that we know. Okay. And so this is the structure of what we're going to do. This is a hint of how we're going to use this. We have some local information. We have some local information about the behavior of f at some particular point. And then from this local information, we can conclude a global statement, a statement about f on the whole of omega. What tool do you know that says something global about something local? Yeah. So by Taylor, we have that f of z is equal to the sum from k equals 0 to infinity of the kth order derivative at w over k factorial of z minus w to the k, and that holds true for all z within the radius of convergence of this Taylor series. And the radius of convergence is actually whatever ball we can fit inside, like this. Yeah? Br of w for any r such that is now going to be written s dot t dot br of w is contained within this thing. Yeah? And that indeed is exactly saying something non-local about something local, because all we need to do to determine these coefficients is look at this one point, w. Right? So we know everything about the function in a ball around w just from knowing exactly what f is like on w. Yeah? So it's a remarkable theorem in that we can look at just one point and look at behavior at just one point, and then we know exactly what the function is going to do in some entire ball around that point. Yeah? You see what I mean, people? Yeah? And that thing is the natural tool to think of because, again, our hypotheses are that we have something approaching one point, and that's all that we know, right? So it could be starting incredibly close to the point already and going towards the point. So it's just an entirely local statement about something happening at one point. Yeah? It's incredibly localized, and we're trying to say something global, something on a large scale. And this is what Taylor allows us to do, right? So we fit this entire ball of radius r inside our domain. Yeah? We can say something about this entire ball based on just the stuff happening exactly at w. Yeah? Cool. All right. So with this, we're going to try and use Taylor's theorem in some way. Okay? We're going to try and use Taylor's theorem. Yeah, it's the natural tool. Okay, cool. So I don't need the exact expression for the derivatives. I'm just going to replace them by ak. It could be that these guys have many of their coefficients are equal to 0, but let's pick the first non-zero one. So let am, or let me just write what these am are. So let's k be these coefficients. So ak is equal to the kth derivative at w over k factorial. And then let am be the first non-zero one. And m is the smallest number for which this is true. So it could be, well, it's not going to be a0 because by continuity we know that f of w equals 0. So it could be a1, yeah, or it could be a2, but whatever. Smallest one. Okay, cool. So that means that we can write a power series like this. F of z is equal to the sum from k is equal to m to infinity ak z minus zk to the k. Yeah? All right. And what information do we have? We have that we have this sequence tending towards w such that f on this sequence is equal to 0. Now look at this. Yeah? And then think about what the consequences of having both of those informations are. So as we let z get very, very close, sorry, w. As we let z be very, very close to w, what is this thing like? What does this power series tell us when we're very, very close to w? Well, yeah, but okay. So where do we get? So okay, little aside. How did you get introduced to Taylor series? Hopefully in the following way, that you all spent a long, long time talking about doing tangent lines, right, in calculus, yeah? And you learned about this is great because we can understand the value of the function very close to the point where we take the tangent line. If this is a, because t of x equals f prime of a, z minus a, plus f of a, that's an incredibly good approximation. We can get an approximation of 101 using the tangent line. You all learned about that stuff. No? Yeah? And for sure, it's true that as we get close to a, then the value of the function gets close to f of a. That's true, of course. Yeah, that's continuity. But this is more refined information. It means that if we are here at some point x, then the difference between the function and the tangent line is way smaller than a minus x. Yeah? Yeah? That's just the tangent line, right? And then if we had something better, if we were allowed to include a quadratic term here, so let's call it q now. I don't mean to write z, I mean to write x. Yeah, then we can do it even better, right? Like this. Yeah? Yeah? And now the difference between this quadratic thing and the actual function is of order x minus a to something much smaller than x squared. So again, it's of order lot smaller than x minus a squared, right? This gap here is way smaller than x minus a squared. Yeah? That's the point of this. Yeah? That's the generalization of a tangent line. Yeah? Just as on a tangent line, we get a much smaller error than x minus a. When we add a quadratic, we get a much smaller error than x minus a squared. Yeah? Cool. So this whole stuff is about being able to replace the value of the function or replace the behavior of the function with something easier to understand. Yeah, so in this case, yeah, everything's going to 0, but the issue is, how is it going to 0? Yeah, how is it going to 0? And generalizing from this idea, this thing should tell us in a better way how this thing is going to 0. It does tell us in a better way how it's going to 0. So how is z going to 0? So how is f of z going to 0 as z approaches w from this? Let's write out the first few terms. am z minus w to the m plus am plus 1 z minus w to the m plus 1. And so on, right? Yeah? Okay, so we have refined information about how this thing is behaving, how it's going to 0 as we approach w. So tell me about it. What do we know about it? Look what this says. Huh? So for z incredibly close to w, what's the significant term here? Good, yeah. So as z gets very, very close to w, this thing is a lot bigger than this thing, yeah? Even though they're all going to 0, yeah? And it's a lot bigger than the next one, yeah? And the next one, and the next one, and the next one, yeah? Yeah? So as z gets very close to w, in fact, what this is telling us is that our function is behaving an awful lot like this thing here, yeah? And the closer we get to w, the more this thing is dominating everything else. This is our equivalent of replacing a function by a tangent line, except that we don't know when this thing starts to be non-zero. So it could be a1, and then it would be the equivalent of a tangent line, yeah? Yeah? But it might not be. It might be that m is 376, right? But it doesn't matter. For small enough, for z close enough to w, that means that the z minus w to the 336 is the dominant term. That's what it behaves like on a small scale. Yeah? And everything else is just a tiny, 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 tiny perturbation of that behavior. Do you see what I mean? Yeah? You all see what I mean? Cool. Okay. So that is the idea. That is what we're going to use. Now look again. Look at this. Look at this stuff here. Why do we have a contradiction from the assumption that we have a non-zero function? At least a non-zero function in the wall.